In this video, we're going to discuss about the critical functionality named triggering for oscilloscope systems. The sole responsibility of the trigger system is to tell the rest of the oscilloscope what exact data to care about. It decides when the acquisition system begins acquiring, which means that by default it decides what is exactly displayed on the screen and what data is available for us to make measurements on. So to bring this definition into context, we'll be playing around with the oscilloscope and the signal on the oscilloscope right now. As you can see from the picture, from the video right now, at the moment, this is a case where the sinusoidal wave is not correctly triggered. So we can see that the signal is very jittery. We cannot make any stable measurement from it. So this is a messed up case. So if I play around with the trigger level and place the trigger level in one of the quote-unquote legit position, we can see that the signal is very stable on the oscilloscope screen. So to understand what triggering is exactly doing for us, we need to discuss two things. The first thing is this. If we zoom in to our curve plot, we can see a little orange triangle here which symbolizes the middle vertical line of all the vertical lines, right? Remember that this 2D plot on an oscilloscope, the horizontal axis is always with respect to time, right? The convention for oscilloscope is that the very middle vertical line symbolizes time zero. So whatever curve you see to the left of this exact middle line happens before time zero, right? And whatever curve shape you see to the right of this line happens after time zero. So this is a convention for almost all the oscilloscopes, right? So let's zoom back. The second thing, let's get the trigger level out of the way first. The second thing we're going to talk about is, before we talk about triggering, is this guy. So this setting actually says that we're using the continuous acquisition mode of an oscilloscope. What it means on a very high level, I'll use an analogy. Basically, the continuous acquisition mode, you can think of it as the oscilloscope being a very high-speed camera. It's trying to take many snapshots of the waveform itself and trying to overlay these snapshots on top of each other. So let's hit stop here. Okay, so this shows one of the random snapshots. So if I move the trigger level around, you can see that a single snapshot contains, with respect to that middle line, right, with respect to a random time zero point, we include like 1, 2, 3, 4, 5 grids to the left. That means 200 microseconds. Remember last video, right? 200 microseconds times 5 is 1 millisecond. We include from minus 1 millisecond to plus 1 millisecond with respect to a random time zero point in the waveform. This is a whole picture, basically. We include all the information from minus 1 millisecond to plus 1 millisecond in this particular setting. right? So this is how we can think of the oscilloscope as really a high-speed camera that's continuously taking many of these pictures and trying to overlay these pictures together. So naturally this brings a question, right? So if we don't have a well-defined time zero point within the period of any periodic waveform, right? If we don't have that well-defined 0 point, then if we really is using a random point on the waveform to take pictures, this is exactly what's gonna happen, right? So the oscilloscope is trying to take pictures, but it doesn't have a good reference point, good well-defined reference point. So each picture is taken would have a phase difference there, right? So when the oscilloscope is trying to overlay all these pictures together, you will see as if it's a movie here. It's really because that all these pictures don't overlay on top of each other because they don't have the same reference time 0 point, right? So this naturally brings in the discussion on triggering. Triggering, what exactly it does is that based on user's input condition, it helps the oscilloscope establish that reference 0 point for quote-unquote picture taking of the oscilloscopes. Okay, let's bring the trigger down here in a legit position and change the trigger type to rising edge trigger type, right? So rising edge trigger type means that, okay, if I set the trigger level, the orange horizontal line on the screen right now is where your trigger level is. So rising edge fixed threshold trigger type means that I'm setting a threshold there, right, as the trigger level says. Whenever the oscilloscope is seeing data points exceeding beyond that trigger level, rising edge exceeding beyond that trigger level, okay, takes that cross point of the trigger level and the waveform to be the time 0 point. Okay, so we can see that for sinusoidal waves, right? If you put the trigger level within the basically within the magnitude of the sine waves, right? Within a single period, there's always one unique point that at that point the waveform is growing beyond, is exceeding beyond that trigger level. There's always one unique point within a period that will satisfy this condition. And if we define that point to be the time 0 point for quote-unquote the snapshot taking of an oscilloscope, then we have a well-defined starting point for all these snapshots. When they're overlaid on top of each other, these curves would overlay on top of each other perfectly, so that you could see a static curve on your oscilloscope screen right now, right? So of course we have many different triggering types. This is the rising edge trigger type. We can also do falling edge trigger type, and as the name suggests, falling edge trigger type really means that, okay, I'm setting a trigger level here. Whenever I see data points falling below the trigger level, we set that point to be the time 0 reference point for quote-unquote snapshot taking of an oscilloscope, right? So let's see something interesting here, right? We do have alternating trigger type and either trigger type. Let's do either trigger type. Either trigger type really means that either the rising edge or the trigger or the falling edge can serve very well as the legit time zero reference point. Right? We can see that there's really two sinusoids here. That's because that still we're in this continuous acquisition mode, and we have two legit starting points for snapshot taking. So this is a very high-speed camera. It takes many snapshots, and it either goes to that rising edge beam, this type, or the falling edge bin. And these two, since we're really doing either type of triggering, edge triggering, so there are really two legit starting point, reference time point for measurement taking in the oscilloscope. So that's why we see this interesting picture on the oscilloscope. So this naturally brings a question also. If we are just using a fixed threshold triggering technique, then there are naturally many signals, not just as simple as sinusoids, that are very hard to be triggered with just a fixed threshold, due to the fact that there may be two or three, there may not be a single unique point that satisfies our triggering condition within a period of the waveform. So we'll be discussing about a special technique of external triggering in the next video, which solve this kind of problem.